conventional notation like this, f gets a prime factor of n. In other words, if n has multiple prime factors, you just give me one. Okay, I don't care which one, just give me one. Okay, if n is 15, you can give me 3, you can give me 5. You know, it's the order is not important at this point, because my objective is to print out all the prime factors. I did not specify in which order. It doesn't have to be in increasing order.
How does it know when next time it loops around which prime factor it gave the last time around?
It does not have to. See, that's the whole point, because n is changed before we loop back over there.
Okay.
So in the let's trace it. Okay, the best way is to trace it. Okay, so let's go ahead and have a second trace. In the second trace, we'll pick a number that has two different prime factors, like 15 is good. Okay, 6, 15, you know, all of those are fine, but I'm just picking 15 here. On line 1, same thing, n is greater than 1 is true, because 15 is more than 1. On line 2, this time, you can take your pick. You can say 5, you can pick, okay, let's pick 3 as a prime factor of 15. On line 3, it's going to print the value of 3 to the screen, okay, or whatever mechanism you have attached to the program. On line 4, what are we doing? No, the other way around. 15 is divided by 3, which gives you a quotient of 5. So n is now updated to 5. As a result, there's no way that I will get confused and say, oh, but have I printed 5 as a prime factor yet? I don't have to worry about it, because the prime factor, as soon as I take care of that prime factor, I reduce the number n, so that it no longer has that particular prime factor. Okay? Now, it might have a prime factor of the same value, like in the case of 4, it is 2 times 2. So it will display 2 twice. But in this case, it will just go ahead and, let me just finish the trace so you can see the whole thing. N is still greater than 1. We go to line 2. This time, what is a prime factor of 5? 5 itself, since it's a prime number. So we go to line 3. We print 5 this time. We go to line 4. 5 divided by 5 is 1. So now n is 1. Then we go back to line 1 again. The condition becomes false, because 1 is greater than 1 is false. And we are done. Okay? So I know that I don't really need to remember what prime numbers I have printed already, because each time I find a prime factor, I divide the number itself by that prime factor. Okay? Which is actually the same way that we did it by hand. Remember when we did it by hand, I used, one line to indicate, so I would say, 35 equals 5 times 7, but the next line will start with 7 equals to 7 times 1. And then the next line will start with a 1, which means I'm done. So do we have any questions about the trace itself of the overall algorithm? But remember, this program is written by a lazy person like myself, who is saying, well, I don't want to specify how to find a prime factor of a number unless I really have to. So I'm going to make a lazy assumption. Let's just say that somebody else knows how to do it already, and I can just copy that code. Okay? But in the process of being lazy, I have just used top-down design, because this means my program is a little bit easier to read than the program that would put the mechanism of finding a prime factor on line 2. Are we okay so far with the concept? It also means that it is easier to come up with this algorithm, because I'm assuming there is a way to find the prime factor of n. So this particular program is only 5 lines long. Okay, and most people can keep track of 5 things at the same time, in terms of programming. So this is not a difficult algorithm by any means. Are we okay so far? Okay. So now, once I realized that I was, being lazy and nobody has specified the logic to find a prime factor f of n, now I have to go through the trouble to try to specify that logic, right? When I specify the logic to find a prime factor given a certain number, do I have to worry about this logic here, the rest of the program? No. I don't. my new algorithm only has to focus on finding a single prime factor of a certain number. I don't have to do the division thing and stuff like that anymore. Are we making any sense? It's kind of like on a map. If I'm planning a trip, from Sacramento to the East Coast by driving, all I have to know is where am I exiting California. Okay, on the bigger map. Once I know where I'm exiting from California, I don't really need to know how I'm getting to the border. Now, when I zoom into the map of California, then I have to worry about, okay, how do I go from Sacramento to this particular border between the states? It's the same thing here. At this point, I'm looking at a map that only displays the states and also the borders between the states, the highways that connect the states. But next time, I will have to zoom into the map of California because I need to know exactly how I can find a prime factor f of n. Okay, are we okay with the approach? What we are doing and why we are doing it? Okay. So now with this out of the way, let me make sure it's all saved. Let's go ahead and try to specify the logic to find a particular prime factor given a certain number. How do you guys do it? Let me go here, start a new web page. So this way, when I save the web page, it is automatically saved in Moodle. 2-1 in class. Okay. How do we find a prime factor given n is greater than 2 and n is an integer?
You're lagging.
No, I'm not lagging. I'm typing ahead. The computer is lagging. Yeah, well, 2-point-something gigahertz apparently is not fast enough to keep up with my slow typing. How do we find a prime factor given that n is greater than 1? Sorry, I couldn't see what I was.
Okay.
Yep. N is greater than 1 and n is an integer. So n starts with 2, 3, 5, 4, 16, and so on and so forth. How do you do it? Now, you guys have all sorts of tricks, right? Yep.
I start with the lowest prime numbers that I know. Mm-hmm. Everybody knows between 2 and 11.
Okay. Well, okay, let me just kind of backtrack a little bit. So you are absolutely right. That's exactly what the program should be doing. But doing that is a little harder, okay, because you need to know the prime numbers ahead of time. Now, if I ask a person to do it, and I say, okay, go ahead and give me a prime factor of this number, 16 in base 10, most people don't have to go through any algorithm to tell me, oh, it's divisible by 2 right away. Because we have these heuristics, rules of thumb to say that if a number ends with 2, 4, 6, 8, 0, it is divisible by 2. That's easy to remember, but that trick only works with base 10 numbers and certain other bases. It does not work with all different bases of numbers. What about this number here? What about, this one that looks kind of nasty? 381. It is not divisible by 2, but you know right away it is divisible by 3. Because when you add up the digits, it is a number that is divisible by 3 itself. Because in this case, 3 plus 8 plus 1 is 12, and 12 is easily divisible by 3. Most people can recognize that right away. What about some numbers like this? Okay, it's a big number, but you know instantly it has to be divisible by 5, because any number that ends with 0 or 5 has to be divisible by 5. So, with people, we have all these little tricks, to tell whether a number is divisible by certain numbers, pretty quickly. And that's why doing that is not going to be helpful, because you cannot write your program to follow and use these heuristics. You can, but it does not make your program any faster. By the time you're done with the heuristics, you might as well not do it. Okay? So that means in order to really figure out the logic to find a prime factor, we have to pick a number that we cannot easily just eyeball the number and say, oh, this has got to be a factor of that number, because that is not going to help when we are trying to specify the logic to do all this. Am I making sense so far? Okay, when you try to create an algorithm, you have to know your own method to do it by hand first. And heuristics, like the ones that I just talked about, they're one, difficult to encode, and two, it really does not help. Because remember one thing, computers don't store numbers in base 10. Okay, and all the tricks that I described, they only work with base 10 numbers. Then someone can say, but you can convert a binary number into a base 10 representation, then apply those rules. But guess what? The conversion process to do that is already longer than finding a prime factor using the other method. So it's not worth doing it. Am I okay so far making my point? Okay. So I will just pick some big number here. Okay. Make sure this number is not easily divisible by 3. Okay, that's divisible by 3 here, and the rest is not. Okay, so I cannot easily tell, there are no easy tricks to tell what is a prime factor of this number. I'm just throwing out a huge big number that I cannot apply those tricks to. So now, what do? You look up Wikipedia and find out whether this is a prime number itself. No, that would not be very useful, because the number of prime numbers only decrease as the value increases. Okay. So what do? Well, assuming that we don't try to use any tricks, we try to divide it by numbers, right? So we'll say 28378281 divided by 2 is. I don't really care about this part. I know the remainder is a 1. Okay? So, do you think 2 is a prime factor of this number? Nope. Okay? So then, what do I do next? We'll try to divide it by 3, and the remainder is going to be something. Okay? We'll call it x. It's going to be... No, it cannot be, because when you add up all the digits, it is not divisible by 3.
It does, that's 39.
39. Is it 39?
Yeah.
Oh, okay. Okay, we'll change it. 39, 40. How about that? 41 this time, so it won't be divisible by 3. Thank you. I added up the number wrong in my head. So, okay, but the whole point is you try to divide it by 3 this time. I don't care about the quotient part. I only care about the remainder part. But the remainder part is going to be different from 0. Okay, so what do you do next? Now, for us, because we are people and we remember certain small prime numbers, what we'll do is we'll try the next one, and most people will say, well, let's skip 4 and go to 5. That's only because, as people, we already know some of the smaller prime numbers. Now, when you're talking about a computer, in order to do the same trick, the computer has to remember the prime factors, the earlier prime factors. Yep?
Well, you can cut out half of them after doing 2 by skipping 2 between these repetitions.
Yes, you can. Yep. But that is also, but that's a trick already as well. Okay? Skipping by 2 is also a trick. So let's just say that we're not going to apply these tricks, because I have another trick up my sleeve that will cut the number of searches down to the square root of the number. So we'll talk about that trick later. So dividing by 5 is a smart thing to do, because dividing by 4 is not going to be helpful. But it also means that your algorithm has to be more complicated, because it has to be aware of the prime numbers already. And we are in the process of trying to factor a number, so you cannot really rely on the fact that you already know some of the prime factors. So that means, I would try 4. And most people will say, but Tech, that's not right. Okay? But when you say that this is not right, you have to tell me how it is not right. Is it not